So the last acid-base titration we want to look at is what's occurring when you're dealing with a polyprotic acid. So polyprotic, we know, of course, means you have more than one hydrogen. So here's an example of a polyprotic acid. That's carbonic acid. And when you put it into water, you could titrate it with, a base of some sort. So let's just kind of look at the titration curve. Let's say we took this polyprotic acid and we reacted it with sodium hydroxide. So we have the polyprotic acid in our flask and we're monitoring the pH change during the course of that reaction. Now we know if we were to do this reaction as a titration, you would have to react 2 of those sodium hydroxides for every one of these carbonic acids, and you would end up with the sodium carbonate as one product and of course water the other product. And so that we can finish that balanced reaction. That's a 2. It doesn't look much like a 2, but that's a 2. All right, so if we look at that, we know that, I've just written that reactionally. I wrote the substances in reverse there. If we cancel out the spectator ions, we see what the net ionic reaction is. So really, the carbonic acid is reacting with 2 of the hydroxides, and we are ending up forming 2 waters and the carbonic acid, the carbonate ion. Okay, so that would be the net ionic equation occurring because the sodium ions are simply spectator ions that are just floating around in solution. Okay, but this overall reaction doesn't happen all in one fell swoop. Really what you do is you end up pulling off the hydrogens with the hydroxide, forming first one water and then reacting with the second one to form the second water. So during the course of this reaction, the first reaction is this, okay, the first, and we're focusing on that blue box right there. So this is reacting with one of those hydroxides. It's 100% pulling off the first hydrogen, leaving me with HCO3 minus and 1 water. So what's happening in our flask? We have our flask and we're monitoring the pH inside of here. Okay, at first we have pure carbonic acid, so we have a pH that is less than 2, okay, and we see that we start adding some of this base and we are converting some of the hydrogen carbonate to, carbonic acid, H2CO3, to some of this. These are conjugates of each other. So we see a rise and a plateau. You see that little bit of plateau? We've got ourselves a buffer range in which we have a buffer solution containing carbonic acid and HCO3 minus. So it rises and kind of levels off, and it comes up to its first inflection point. The first inflection point is when you no longer have any of this, it's gone, and you have pure HCO3 minus. Well, that right there is going to be able to, if we look at the pH there, we see at the pH it's 4 looks like it's about a 5, okay? So we've got ourselves an acidic solution. It is still a proton donor, still able to donate. All right, so that's the first range. Now, once you've done that, then the second reaction can happen. We can take that HCO3 minus and we continue to add OH to it. As we continue to add OH to it, it's going to be able to pull off the second proton and form CO3 2 minus and the water. So as we use up all of this and convert it to that, then this is able to continue to react and we form our second region there. Okay, so during this second region we end up forming this carbonate ion. Well, this one is going to have a pH at this range that is greater than 10. It's going to take the exact same amount of hydroxide to reach that first inflection point, the first equivalence point, as it does to reach the second equivalence point. And we see in our diagram there, it took about 25 milliliters for each of those. So that's how it changes. Now, what do I expect you to know about the titration curve? Well, you ought to be able to recognize when you're given a titration curve like this that it's a polyprotic acid that you're titrating, because you've got those multiple inflection points, those equivalence points where they're rising. Okay, so that's really, we're not calculating along the graph there, we just recognize the titration curve. So what are we going to look at next? Well, when we do a titration and we're adding a base to our acid, we're trying to find the point at which you reach that equivalence point. We're trying to find when do you have equal amounts of the acid and the base. Well, you have to add indicators in order to do this, or that is at least one way to do that. These are things that will change color with pH. So what we're going to look at next is how these indicators work. What are they and how do they work?